Okay, welcome back to Feedback Control Systems. This is Module 5.3. We're going to talk about signal flow graphs and Mason's rule. The objectives of this module are to describe signal flow graphs, then look at a conversion between these signal flow graphs and block diagrams, discuss Mason's rule, provide an example of Mason's rule, and then finally end up with generating signal flow graphs using state equations. So first, signal flow graphs, a little bit of nomenclature to start with here. For signal flow graphs, we are going to use the following conventions. For a system, for example, G of S, we're going to use a straight line with the nomenclature of G of S notated on that line somewhere. And then a signal will be denoted as a node, in this case, V of S. And so we can see the interconnection of the signals and systems as shown here. So for example, I might have an input R1 of S that goes through G1 of S and to this signal node Vs. I might also have additional inputs, R2 and R3, going through their transfer characteristics. Notice G2 in this case has a negative sign, so that could be there as well. And then finally, from that node, maybe I have a variety of outputs, C1, 2, or 3, again, going through their own characteristic system as shown there. So let's start with an example. This will be a cascaded system. So I have an input on the far left, R of S, and then an output, C of S, on the far right. So in this cascaded system, I have G1, G2, and then G3. So Rs times G1, as shown here, I might call that this intermediate variable x2 of S. That then will feed into G2, and so that will become another intermediate variable x1 of S, which we could write first in terms of the input Rs, which is just G1 times G2, or we could also write x1 of S in terms of x2, which would be x2 times G2. And then finally, C of S, again, in terms of the input, it would be the product of all of those transfer characteristics, or we could also write it in terms of x1 or x2. Converting that to the signal flow graph down below, we see we have an input signal Rs, an output signal here Cs. We show the three transfer characteristics, and then the three intermediate signals, two intermediate signals V1 and V2, as shown on the graph. Assuming we would like to pick those off, measure those, for example, we could do that as shown. Okay. We could also look at signal flow graphs for a parallel case. And so for the parallel case, maybe they all have the same input Rs, and they then go into parallel paths. So G1, G2, and G3. Each of those might have these intermediate variables x1, x2, and x3. As you can see, their definitions is shown there. And then finally, at the output, C of S, now that comes to a summing junction, and so each one could either be represented with a positive or negative signal, as shown there. So we'll leave it up to you if you want to make these all positive or all negative or mix and match. We'll leave that up to you depending on the application. Now, taking that block diagram and then converting it over here to our signal flow graph, we have our input signal Rs, our output signal Cs, and then you can see the various paths that come through. So what I might do, notice here I have V1 of S. Well, I could call this signal V1 of S right there, the middle signal V2, and then the bottom signal here V3. And so notice if I have those defined here, they're all going to a summing junction, and then so notice the transfer characteristic here. I just multiply those signals by 1, or if there was a negative sign, I could multiply by -1 relative to that summing junction. Okay? And then finally, we could look at a feedback example where, in this case, I have a single input Rs. I'm looking at my output, but now the output gets fed back through a transfer characteristic as shown there. Converting that, I have my input signal Rs, my output signal Cs, and as I look here, notice that the output signal gets multiplied by H of S with the negative sign. Notice the negative sign on top. I'm going to assume there's a negative sign for negative feedback. That then comes to this signal right here, which is our error signal. So I have Rs times a gain of 1. Again, as a positive 1 coming in, and then a negative HS, so those two get combined, forms an error signal, E sub S. That then gets multiplied by the plant controller G of S combination that I'm showing there. Okay? Now let's assume that we are showing this block diagram. We're going to convert it to our signal flow graph as shown. So we have some feedback, maybe some parallel paths going on here. So there's a lot going on. So let's see how we could break this down. Okay. So first of all, what we could do is let's start with our inputs, R sub s as shown here. And notice R sub s comes into this summing junction right there as a positive. So that's that summing junction right there. To the right of the summing junction, we call that signal V1 of s. Now, below that, we see V6 of s with the negative sign, and we see that down here as well. V1 then gets multiplied by G1, as we see on the line characteristic right there. That then forms us into V2. Okay? And then we could kind of progress as we go through this. For example, I'll start at the output and kind of work backwards a little bit. So here's our output, C of S, as we show here. Notice the formation of C of S, it's V5 times G3, which is this signal right here times G3. Also notice that CS gets fed back to V8 via H3 as shown here, and then V8 gets subtracted right there to form that signal V5. So again, I've started on either end. I'll leave it to you to kind of close in and look at the other paths based on the previous examples we've worked to see if you can finalize that signal graph. Okay, so I'm going to clear some of this ink here, and then as I look forward, that signal flow graph, maybe I don't need some of these intermediate signals. So for example, if I don't need to measure, for example, V2 specifically, or V6 or V7 or V8, notice what's happening with those signals. V6 no longer appears down here, but instead what do I have? I have here H1 of S with the negative 1. I'm going to combine them into negative H1 of S there. So depending on either of the signal flow diagrams are equivalent, but maybe if they're, again, signals we don't really care about as much in our application, we could reduce and simplify, again, from a look and feel of what the signal flow diagram will look like. They're both, again, equivalent. Next, I'd like to get into Mason's rule. We'll read through some of the definitions assigned here, and then we'll dig in a little bit deeper. So Mason's rule is going to be a technique for reducing the signal flow graphs down to a single transfer function. So if you think of the previous slide, we could take that signal flow graph, whether the more full representation or the simplified one, and equate that into an actual transfer function. So some definitions here. First, we have the loop gain. Now, the loop gain is defined as the start at a node. We're going to start at a specific node. Then we're going to return to the same node without passing through another node more than once. So, for example, we'll start here. We might progress down a path and then form some feedback path to come back to it. So we might pass other nodes along the way, but as long as we pass through them only once, that will be referred to as our definition of loop gain. The second definition, the forward path gain, is the product of the gains of the transfer characteristics found from any input node to output node. So if I have a single input, a single output, I'm just going to have one forward path gain. If I have multiple inputs, then I would have to take each one separately going to the single output, or I could have multiple outputs, and you can see from there we might have multiple forward path gains. Next is what we're going to call non-touching loops. So we may have a variety of feedback loops, maybe one here, another one over here, that do not touch or interact with each other. They don't share a common node. Those are going to be referred to as non-touching loops. And then the final definition here, the non-touching loop gain. These are going to be the product of loop gains from the non-touching loops taken either 2, 3, or 4 at a time. So for example, we might just have 2 non-touching loops. We may have 3 non-touching loops. We're going to take those individually, and these definitions, I believe, are going to be much clearer as we work an example coming up shortly. First, before going to that example, in red we show the definition in terms of how we can reduce the signal flow graphs to a single transfer function. So here is the transfer function. We are interested in showing the input output relationship here, the output C of S, the input R of S. And that is of this form here. So the first term here, it's the sum of K. So first of all, what is K? K is going to be the number of forward paths, okay? Number of forward paths that we have. And again, if I look forward path gain, a forward path goes from an input node to an output node. So that's going to be k. T of k, the second term here, is going to be the kth forward path gain. So we'll, again, best explained with an example. Then I have a delta k and a delta, as you see here. So first we'll start with delta. Delta is going to be the number 1 minus the summation of all of the individual loop gains. Then notice, so first I subtract, then I go plus the non-touching loop gains 2 at a time. Then I'm going to subtract non-touching loop gains 3 at a time. Then I'm going to add non-touching loop gains 4 at a time, etc. So notice that I have alternating signs. So I go minus, plus, each time adding additional non-touching loop gains, 2, 3, 4, etc. So again, my guess is you're maybe just a little bit fuzzy or a little confused with some of these definitions. We have an example on the next slide that'll hopefully make this a lot clearer. And then finally, our delta sub k is going to be 1 minus all of the loop gain terms associated with delta that touch the kth forward path. So the easiest way to describe delta k, let's say k is 1. I have a single input, single output, one forward path gain, one forward path. What this term delta k says is anything that's not touching that forward path. So if I have a loop down here, right, I have a feedback loop and then there's like another feedback loop, etc. As long as that's not touching that, that will remain. Everything else that touches that forward path will be eliminated, okay? So that's kind of the overview. And again, let's go right to an example, okay? So here is the signal flow graph here. I have my input RS on the left, my output CS on the right, and you can see I have a bunch of G1, G2, all the way up to I think G8, a couple of feedback paths, H1, H2, H3, etc. Here, so that's sort of the high level. So the first thing we want to do is, on the previous slide, we want to identify K. And in this case, K is 1. I have a single input, R sub S, single output, C of S. So I basically have one forward path. K equals 1. So the forward path gain, T sub K, in this case T of 1, there's only one forward path gain. I start at the input, R of S, and then I multiply G1 times G2 times G3 times G4 times G5. That's what you see here. I multiply all of those gains going in the forward path. That is my T1 of S. If I had a second input going to that output, I would have a T sub 2, and I would calculate that as well. But for this example, we only have that one forward path. So let me clean that up. Next, I want to do, beyond the forward path gains, I want to look at what we call the loop gains. So the loop gain is shown here. I have 4 of them. I have G2H1. So I start at a node, V4 in this case, and I look for my loops. I end up back at that node, and I can touch a node only one time. Okay? So G2 to H1 is my first one. G4H2 is my second one. I have a G7H4 right here. And then look at this big one. If I start at this node right here and go all the way around, so in this case, G2, G3, G5, G4, G6, G7, and G8, I can only touch each node once. That's what this one is. So all around, 3 minor loops and then one big loop coming back. So those are my various loop gains. Again, starting at a node, return to that node, and then I can only touch the other nodes one time. Okay? Now I'm going to get to what we call non-touching loops 2 at a time. So let's clear some ink again. So first I want to identify what are 2 non-touching loops. 2 non-touching loops. And so first I'll call it loop 1 and loop 2. So here's loop 1, G2 and H1. Here is loop 2, which is G4, H2. So that's what you'll see here in this calculation, is I'm taking 2 loops that are not touching, and multiplying them together. So that is one combination. The next combination would be loop 1 and 3. So here's loop 1, this is loop 2, and this here is loop 3. Okay? So those are my two non-touching loops. So I'm going to go 1 and 2, 1 and 3, and then 2 and 3. All of those products is what you'll see here. Okay? And then finally, those are my non-touching loops 2 at a time. Now I want to look at my non-touching loops 3 at a time. So in this case, I have 3 loops that do not touch, loop 1, loop 2, loop 3. So I just take those loops, multiply them together, and that's what you'll see right there. Okay? And if I were to have, for example, another loop here, that would be 4, I would do that. So I've now basically completed what I have here. Now I'm going to go for my delta. My delta from the previous slide, start with the number 1 minus what? So I go minus, and all this stuff right here, all of this stuff is what? All of my loop gains. So these are all of my loop gains. 1 minus all of the loop gains. Okay? And then I go plus what? My non-touching loops 2 at a time, so that's this next stuff right here, all of this. So plus all of that, and then minus non-touching loops 3 at a time, which is this. That goes there, okay? So that's how I create delta. Now, if you can imagine, all of these G's have a transfer characteristic, like 5 over s squared plus 2s plus 4 or something like that, and I have all this. This is going to be some really messy algebra. So we'll leave that to you as we go through to work on some algebra. But this is, again, the formulation of how you would do that. Okay, so that's our delta. And then finally, our delta sub k. Remember, k is just 1. And so in order to find delta 1, it's 1 minus everything that doesn't touch that forward gain. So really, here's our forward gain. We're eliminating everything else that doesn't. So the only thing we have left relative to that loop gain is that term right there. So the G7 and H4. So that will be our delta 1 value that we have. Okay? Now, finally, with all this information as background, I can calculate my transfer characteristic using the information on the previous slide. So I'm going to sum over k, but in this case, k of 1, T1 times delta 1. Well, T1 is up here. Delta 1 is right here. So I just literally will multiply those two together. That's what's in the numerator. The denominator is delta. So delta, you can see right here, or the definition. I can just put that right there. So again, I could write all that out. You're going to see it's some very, very messy algebra. So you can use a variety of programs for this. Once you've defined these in a program such as MATLAB or some other thing that may have some symbolic calculation, it can do that for you. Okay? So just wanted to walk you through Mason's rule and an example of how to approach that. So the last topic of this module is to look at signal flow graphs of state equations. So I've listed the state equations here. And remember, the state equations represent first-order differential equations in the time domain. And so here I have 3 state variables, x1, x2, and x3. And then I have an output here, y, expressed as those state variables. So in order to create signal flow graphs, the approach I'm going to take here is the following. Well, I have some input r, which I'm going to, in the time domain, notice the small r goes to a capital R of s in the Laplace domain. So that's my input, r of s, and then I have my output, y of s right here. So we've also called that C of s, etc. But for state equations, we typically will show y. Then what I want to do is I want to put in my 3 state variables, x1, x2, and x3. So that's what you'll see here, as well as their sort of derivative s times x1. So here's x2 and then s times x2 and then x3, s times x3. So I'm going to start by creating those nodes right there. And then what I'll do is I want to form x1 dot. So x1 dot, our top equation here. So what I'm going to do is I start with this, then I'm going to take it down, and then I'm going to start filling it out based on x1. So x1 equals what? Well, from an input perspective, it's 2 times r. So where is x1 dot? X1 dot, excuse me, let's erase some of the ink. It's getting a little messy. Okay, so where is x1 dot on this graph? Well, that's this dot right there. That's that circle. So notice it's a function of the input, which is 2r. So here is my 2r, summing in right there to my x1 dot. It's also a function of 2x1. So here's my x1 and my 2x1 kind of summing back. And then I have a minus 5x2. Here's my minus 5x2. And then I have a plus 3x3, which is shown right there. So that's basically my formulation of my x1 dot. Next, I can form my x2 dot in a very similar way. Here's my x2 dot. And my x2 dot is going to be right there. So on this graph here on the right, I've left my x1 dot there, and now I'm going to build upon that with my x2 dot. So again, I can see it is 5 times the input. So 5 times that input sums in as shown there. And then again, I'll leave it to you to kind of go through the rest of them and see how those graphs go in. So I have a negative 6 relative to x1, and then I have a negative 2 with regard to x2, and then a 2 with regard to x3. I can similarly do the same thing for x3 dot as shown there. And again, I will leave that as an exercise for you to say, here's x3 dot, which is right there. You'll see 7 times r, which is right there. And then you'll see all the additional terms as we go from there. And then finally, what we can do is form the output y. Here's our y. Notice y is negative 4x1. So here's negative 4 times x1. And then I have a 6x2 and then a 9x3 that all sum in to form my y. So that lower right corner represents the final signal flow diagram based on the state equation. So I think if you follow this sort of procedure, first start here with the nodes, the state variables, and their derivatives, and then slowly add one state variable at a time, that you can slowly build up to this in a very methodical, logical way, and then form your final state diagram that we have shown here. So that will complete this module. If you happen to have any questions on this, please don't hesitate to reach out. Thank you.